I've already started with the eye color example, so I figure no harm in continuing it. Let's say we live on a planet or we're a species where there's only two possible eye colors, either blue, and the genotype or the allele for blue I'll abbreviate with a lowercase b, or you could have brown eyes. Brown eyes. I'm doing it in the salmon color just because I got tired of the brown. We'll do it uppercase B. And I'll make a few other simplifying assumptions. First of all, let's just assume that this is a kind of a simple, the expression of this gene is very simple, that brown is dominant to blue. So if you have one of each, you're going to see brown eyes. The only way you're going to see blue eyes is if you have a blue allele from each of your parent. And then the other assumptions I'm going to make is that this population is essentially has a stable gene pool for this with respect to the eye color gene. And what do I mean by that? No selection. No selection is taking place. No natural selection. So based on this trait, so for example, you're not more or less likely to be able to reproduce, or the number of children you have is not going to be larger or greater, dependent on what your eye color is in this population. And I'm also going to assume that there's no mutations. No mutations. So for whatever reason, a chromosome that has a blue allele can't randomly turn to a brown or vice versa, or turn into a third color. And I'm also going to assume I'm going to have a large population. Large population. And the reason why I'm making all of these assumptions is because I essentially want to have a stable gene pool, at least relative to this gene. Relative to the eye color gene, I want to be stable. I want to have a stable allele frequency. What do I mean by allele frequency? Allele frequency. I mean that, like, well, I said large population, but let's take a very small population. Let's say that there's two people in the population, and one guy right here is, I'll just do it in a neutral. Well, let's say his genotype is big B and lowercase b. And let's say that the other guy has blue eyes, so he has to be homozygous recessive. Let's say this is the entire population. Of course, a population of 2 can't apply to what I'm about to do, but I just want to explain allele frequency. The allele frequency here of the blue eyes, the blue-eyed allele frequency here, is what? Well, in this population, I have exactly 4 alleles. I only have 2 individuals, but they each have 2 alleles. So it's going to be 75%. 75% of the alleles in this population are blue. Right? There's 1, 2, 3, 4 alleles, and 3 of them are blue. The frequency of the brown allele is 25%. And this is different than the actual expression. If I asked you the frequency of brown eyes versus blue eyes, so this is allele frequency. Let me write that down. That's allele frequency right there. If I were to ask you phenotype frequency, so let me do it. Phenotype. If I said what percentage of how frequent are blue eyes seen in my population, blue eyes, well, it's only 1 out of the 2 people in my population, so you'd say it's 50%. And then for brown eyes, you'd say it's 50%. Brown eyes, you'd say it's 50%. So I want to make this distinction very clear, because it's going to be very confusing when people talk about allele frequency. Allele frequency is literally if you were able to go and look at the actual genotype, the actual chromosomes of every person in the population, and count how many of them had the blue allele versus the brown allele, you would come up with this number. This is different than the actual phenotype frequency. Now, all of that is just as a background, because if I have this, these set of assumptions are true, and my population isn't in any way evolving, then my allele frequency is going to be roughly constant. And I had to assume a large population, because a small population, just from random chance, my allele frequency could start to change. But let's say that my allele frequency is constant, then I'm in a Hardy-Weinberg equilibrium. Hardy-Weinberg equilibrium. And all this is a situation where the allele frequency isn't changing. Equilibrium. And the reason why we're making all of those assumptions is because if we can assume this, we can start to deduce some things about given what we observe, what must be the genotypes in the population or the frequencies of different phenotypes and whatever else. So for example, if P is the frequency of blue eyes, so let me say P is equal to the frequency of blue eyes, and Q is equal to the frequency of brown eyes, what's P plus Q going to be? What's P plus Q? Well, everything is either going to have blue eyes or brown eyes. If this is 50%, if this is 20%, and remember, this is the allele. Let me make the B allele. Let me make that very clear. This isn't necessarily what you observe. This is the allele itself. This is the allele frequency. If you were actually to count the chromosomes and see which ones, what percentage have the blue allele and what percentage have the uppercase brown allele. Well, every chromosome has to have either of those, so these are going to add up to 100%. 100% or equal to 1. For example, if 30% of the alleles are blue, then 70% are going to have to be brown, because I already told you at the beginning of this video that we're in a world where you either have a blue allele or a brown allele. Now, what if we don't care about alleles? We actually care about the frequency of the genotypes. So there's a couple of things we could do. We could literally just square both sides of this, and then think about what that gives us. So if we square both sides of this equation, you get what? P plus Q squared is P squared plus 2PQ plus Q squared, and you square the other side, and it's equal to 1 as well. What does this tell us? What is P squared? Well, it's the probability that I get 2 of the lowercase blue alleles, right? What's the probability that I get 2, that I end up with lowercase b is my genotype? Well, I have to get a lowercase b from my first parent, and that's with the probability of P. And then a lowercase b from my second parent with the probability of P. So it's P times P, so that's P squared. What's Q squared? Well, that's the probability that I get a big B, a brown-eyed allele from each parent, because the probability from parent 1 is Q, and then the probability from parent 2 is also Q. So that's Q squared right there. Now, what's 2PQ? Well, that's essentially this entire term is the frequency that I'm a hybrid. I have a heterozygous genotype. And why is that? Because there's two ways that I can be a heterozygote. I could be like this. I want to do that other blue. I could get blue eyes from one parent and brown eyes from the other. Or I could get brown eyes from the first parent and blue eyes from the second. And I don't know anything about these parents, so if everything is, if I'm making no assumptions, then I just have to assume that the probability that I get an allele from either one of them is equal to the frequency in the population. So there's two ways of getting these. The probability of each of these ways, the probability of this combination is P times Q. The probability of this is Q times P, which is the same thing. And you add them together, you get 2PQ. So this is essentially the frequency of the hybrids in the population. So let's see if we can, I've been kind of abstract so far. Let's see if we can apply this to a real world problem. And obviously I'm making some simplifying assumptions. Let's say that we go into a population, let's say it's a population of 1 million people, reasonably large, and we observe that 9% have blue eyes. Blue eyes. This is their phenotype. This is the frequency of the genotype b lowercase b. Right? I started with this phenotype blue eyes, but I know since blue is a recessive trait that they must have 2 copies of the recessive allele. So this is the frequency. The frequency of having 2 lowercase b's is 9%. Well, if you just look here, I just showed you that that's also equal to P squared. P squared is equal to 9%. And how do you think about that? Well, P is the probability of getting a blue allele. It's the frequency of the blue allele in the population. In order to get 2 of them, you have to multiply P by itself twice. So what's the frequency of the blue allele in the population? P is equal to the square root of 0.09, which is 0.3. So if you went and actually counted all of the alleles in the population, you would actually find that 30% of them are the lowercase blue. Now, a much smaller percentage of people, only 9%, show the blue eyes because you need 2 of them. You have a 30% chance of getting it from your mom and a 30% chance of getting it from your dad. So what's the probability of, what's the frequency of a brown-eyed allele? So what's the frequency of the brown-eyed allele? Well, we know that the frequency of the blue eyes plus the brown eyes is 100%, so that's going to be 70%. If 30% of all of the chromosomes, or of all of the alleles in the population are blue, the other 70% are going to have to be brown. So what percentage of my population are going to be, oh, there's a couple of things we can do. What percentage of my population are going to have, well, I'll do an easy one. What percentage of my population are going to have brown eyes? So if I just look at the phenotype, brown eyes. I don't even have to use any of the formulas for this one. I already told you 9% have blue eyes, so the rest must have brown eyes. So 91% have brown eyes. Have brown eyes. Now, we just said we have 9% have blue eyes, 91% have brown eyes. What percentage of the population are going to be homozygous for brown eyes? So they need to have the capital B from both parents. Well, we know that the frequency of the capital B allele is 70%. So what percent are going to be homozygous dominant? Let me draw that. Homozygous dominant. Well, the frequency, it's going to be Q squared. They're going to have to get a Q. They're going to have to get a uppercase B from each parent. So that's going to be 0.7 squared, which is equal to 0.49, or 49%. 49%. So just starting already from that one idea, that 9% have blue eyes, we've already been able to deduce that 91% must have brown eyes. And of the 91% of the brown eyes of the whole population, 49%, this isn't 49% of the 91, this is 49% of the population, 49% are homozygous dominant. And then what percentage of the population are going to be hybrids? Well, hybrids also have brown eyes, but they're not homozygous dominant. So what the remainder here? So what is that? That's 42%. 42% are going to be hybrids. And if we go back to the Hardy-Weinberg equation, we see that. So we get, P plus Q has to be equal to, well, 100%, or I could just write equal to 1. And we figured out that P was 30%. That's the frequency of the blue-eyed allele, the actual trait, not the observation of it or the genotype. And the frequency of the brown eyes was 70%. And then this is actually a breakdown when you square that. So we also know that P squared plus 2PQ plus Q squared is equal to 1. This is the percentage of the population that has blue eyes. They have 2 blue alleles, so that's 9%. This is the percentage of the population that has 2 brown alleles, homozygous dominant. So that is 49%. And then this is the remainder, this 2PQ, this whole term right here is what's left over. So let's see, 9 plus is 58. This is going to be 42%. 42% are hybrids. And if I just talked about phenotypes, I'd say 9% have blue eyes, and then the remainder, 91%, have brown eyes. So hopefully you found that reasonably useful. Just from kind of very simple deductions, it's almost it's almost kind of silly that this is almost a separate principle, because you can kind of deduce this from very basic ideas, and you can square both sides of that. But you can come up with some fairly fascinating results about what's going on in a population, because what we can observe maybe the frequency. Let's say some disease only happens when someone is homozygous recessive. So you can go and see, okay, what percentage of the population has that disease. But then doing the math that we just did in this video, you can figure out what percentage of the population have the allele for the disease, they're carriers for the disease, but they don't actually show it, and that would be the hybrids right there. So this is actually a pretty powerful tool you've just learned.